The National Electrical Code, or NEC, Section 300.15b requires plastic bushings for all conductors larger than number 4 American wire gauge, or AUG, in polyvinyl chloride, or PVC conduits. This is to protect the conductors from damage caused by the sharp edges of the conduit. However, electricians sometimes face challenges in installing these bushings, especially on larger conduits such as 4-inch PVC. After the lock nut is tightened, there is limited space for the threads to engage, and the bushings can become loose during wire pulls. There are several possible solutions to this problem. Firstly, consider using oversized bushings. Using plastic bushings designed for larger conduit sizes, such as 6-inch bushings on 4-inch conduits, provides more threads for engagement. Secondly, install bushings before pulling wires. If possible, install the plastic bushings and the male adapters before pulling the wires. This ensures the bushings are securely in place before any force is applied. Thirdly, secure bushings with tape. If pre-installation isn't possible, secure the bushings with electrical tape after tightening the lock nut to prevent them from coming loose. Fourthly, use 2 bushings. Install 2 plastic bushings stacked on top of each other to extend the number of threads available for engagement. Fifthly, consult with the inspector. Discuss the situation with the inspector and seek their guidance on acceptable solutions. They may be willing to make an exception or suggest alternative methods. In addition to these solutions, several other factors should be considered. If using thermoplastic high-heat nylon, or THHN, or cross-linked polyethylene high-heat water-resistant, or XHHW conductors, which are relatively stiff, the bushings may be less likely to come loose during a pull. Also, ensure that the conduit is not overfilled with wires, as this can put additional strain on the bushings. Finally, use high-quality plastic bushings that are made of durable materials and have a good fit. Selecting the correct size and material for the electrical wiring is determined by its ampacity based on the American wire gauge, or AUG. The National Electrical Code, or NEC, publishes tables of allowable ampacities for insulated conductors. These tables account for the wire material, its insulation type, and the ambient temperature. The NEC table number 310.15b16 is a crucial reference point. The table details the ampacities of insulated conductors rated up to and including 2000 volts, with temperature ratings of 60 degrees Celsius to 90 degrees Celsius. These conductors are installed in raceways, cables, or directly buried in earth. The ampacity is the maximum current, measured in amps, that a conductor can carry continuously under specified conditions without exceeding its temperature rating. Exceeding the ampacity can damage the insulation, leading to short circuits, ground faults, and potentially fires. The table lists ampacities for various wire sizes and insulation types. For instance, a number 12 AWG copper wire with THHN insulation rated for 90 degrees Celsius might have an ampacity of 30 amps under certain conditions. However, it is essential to understand that the ampacity values in NEC table number 310.15b16 are based on specific conditions. Adjustments must be made to these values based on ambient temperature and the number of current carrying conductors in a raceway or cable. If the ambient temperature is higher than 30 degrees Celsius, the ampacity must be derated. Derating factors are provided in NEC table number 310.15b2. Similarly, if there are more than 3 current carrying conductors in a raceway or cable, the ampacity must be derated according to NEC table number 310.15 cone. These adjustments ensure that the conductor temperature remains within its insulation rating, preventing premature failure. For example, if a number 12 AWG THHN copper wire is installed in an ambient temperature of 40 degrees Celsius, the ampacity may need to be reduced by a certain percentage. Likewise, if there are 6 current carrying conductors in the same conduit, the ampacity would need to be further reduced. The NEC defines different types of insulation for conductors, each with a specific temperature rating. Common insulation types include THHN, THWN, XHHW, and UF. THHN insulation is commonly used for dry and damp locations, with a maximum temperature rating of 90 degrees Celsius. THWN insulation is suitable for wet locations and has a maximum temperature rating of 75 degrees Celsius in wet locations and 90 degrees Celsius in dry locations. XHHW insulation is cross-linked polyethylene and is suitable for both wet and dry locations, with a maximum temperature rating of 90 degrees Celsius. UF insulation is underground feeder cable, suitable for direct burial in earth, and has a maximum temperature rating of 75 degrees Celsius. The choice of insulation type depends on the application and environmental conditions. The NEC also specifies requirements for conductor insulation, including the type of raceway or cable to be used. Raceways, such as conduit, provide physical protection for conductors and can be made of metal or non-metal materials. Metal conduits, such as rigid metal conduit, or RMC, and electrical metallic tubing, or IM, provide excellent mechanical protection and can also serve as equipment grounding conductors. Non-metal conduits, such as PVC, are lightweight and resistant to corrosion but require a separate equipment grounding conductor. Cables, such as non-metallic, or NM, cable and armored cable, or AC, consist of insulated conductors enclosed in a protective jacket or armor. NM cable is commonly used for residential wiring in dry locations, while AC cable is suitable for both dry and damp locations. Grounding is a critical aspect of electrical safety, and the NEC provides detailed requirements for grounding conductors and equipment. Grounding ensures that metal enclosures and equipment are at the same electrical potential as the earth, preventing electric shock hazards. The equipment grounding conductor, or EG, is a dedicated conductor that connects metal enclosures and equipment to the grounding electrode system. The size of the EGC depends on the size of the circuit conductors, as specified in NEC table number 250.122. The grounding electrode system typically consists of a ground rod, ground plate, or metal water pipe that is connected to the earth. The grounding electrode conductor connects the grounding electrode to the electrical system's neutral point, providing a low impedance path for fault current to flow back to the source. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. These devices interrupt the flow of current when it exceeds a safe level, preventing damage to the wiring and equipment. The size of the overcurrent protection device must be matched to the ampacity of the conductor being protected. NEC section number 240.4 provides rules for overcurrent protection, including the maximum allowable size of the overcurrent protection device for different conductor sizes. For example, a number 14 AWG copper wire is typically protected by a 15 amp circuit breaker, while a number 12 AWG copper wire is protected by a 20 amp circuit breaker. Understanding and applying the requirements of NEC table number 310.15b16 is essential for ensuring the safe and reliable operation of electrical systems. It is important to consult the latest edition of the NEC and to seek guidance from qualified electrical professionals when designing and installing electrical wiring. This detailed approach ensures that electrical installations meet safety standards and operate efficiently. When dealing with electrical components, the voltage drop calculation becomes critical to ensure the performance of the electrical system. The voltage drop refers to the reduction in voltage that occurs as electrical current flows through a conductor. Excessive voltage drop can lead to inefficient operation of electrical equipment, dimming of lights, and overheating of conductors. The National Electrical Code, or NEC, recommends that the voltage drop in branch circuits should not exceed 3%, and the voltage drop in feeders should not exceed 5%. Branch circuits are the circuits that supply power to individual outlets, lights, and appliances, while feeders are the circuits that supply power to branch circuits. To calculate voltage drop, several factors must be considered, including the length of the conductor, the current flowing through the conductor, the resistance of the conductor, and the conductor's voltage. The voltage drop can be calculated using the following formula. Voltage drop equals 2 times the length times the current times the resistance divided by 1000. while length is the length of the conductor in feet. Current is the current flowing through the conductor in amps, and resistance is the resistance of the conductor in ohms per 1000 feet. The resistance of the conductor depends on its material, size, and temperature. Copper conductors have lower resistance than aluminum conductors, and larger conductors have lower resistance than smaller conductors. The resistance of conductors increases with temperature, so the voltage drop will be higher at higher temperatures. To minimize voltage drop, several steps can be taken. Firstly, use larger conductors. Larger conductors have lower resistance, which reduces voltage drop. The NEC provides tables that specify the minimum conductor size for different ampacities and voltage drop requirement. Secondly, shorten the length of the conductor. Shorter conductors have lower resistance, which reduces voltage drop. This can be achieved by locating the electrical panel closer to the loads or by using multiple circuits to distribute the load. Thirdly, reduce the current flowing through the conductor. Lower current reduces voltage drop. This can be achieved by using more efficient equipment or by balancing the load across multiple circuits. Fourthly, use copper conductors. Copper conductors have lower resistance than aluminum conductors, which reduces voltage drop. However, copper conductors are more expensive than aluminum conductors, so the cost must be considered. Fifthly, use higher voltage. Higher voltage reduces the current required to deliver the same amount of power, which reduces voltage drop. For example, using 240 volts instead of 120 volts for a circuit will reduce the current by half and reduce the voltage drop by half. The NEC provides guidelines for selecting conductor sizes based on voltage drop requirements. NEC section number 215.2 ATHP provides requirements for feeder conductors, and NEC section number 210.19 AOM provides requirements for branch circuit conductors. These sections specify that the conductors must be sized to limit the voltage drop to the recommended levels. In addition to calculating voltage drop, it is also important to consider voltage drop when selecting electrical equipment. Electrical equipment is designed to operate within a certain voltage range, and excessive voltage drop can cause the equipment to malfunction or fail. For example, motors may overheat and burn out if the voltage is too low, and electronic equipment may not operate properly if the voltage is too high or too low. To ensure proper operation of electrical equipment, it is important to select equipment that is compatible with the voltage and to minimize voltage drop in the circuit. This may involve using voltage regulators or other voltage correction devices. In summary, voltage drop is an important consideration in electrical system design and installation. By understanding the factors that affect voltage drop and taking steps to minimize it, electrical professionals can ensure that electrical systems operate efficiently and reliably. The NEC provides guidance on voltage drop requirements and conductor sizing, and it is important to consult the NEC when designing and installing electrical systems. When using PVC conduit, it is essential to understand the expansion characteristics of the material. PVC conduit expands and contracts with temperature changes, and this expansion and contraction can put stress on the conduit system and the conductors inside. The National Electrical Code, or NEC, provides guidelines for accommodating expansion and contraction in PVC conduit systems. The coefficient of linear expansion for PVC is relatively high compared to other materials such as steel. This means that PVC conduit will expand and contract more for the same temperature change. The amount of expansion or contraction depends on the length of the conduit, the temperature change, and the coefficient of linear expansion. To calculate the amount of expansion or contraction, the following formula can be used. Expansion equals the coefficient of linear expansion times the length times the temperature change. Where the coefficient of linear expansion for PVC is approximately 0.3 per degree Fahrenheit, the length is the length of the conduit in inches, and the temperature change is the difference between the minimum and maximum temperatures in degrees Fahrenheit. For example, if a 100-foot length of PVC conduit is installed in an area where the temperature can range from 20 degrees Fahrenheit to 120 degrees Fahrenheit, the amount of expansion can be calculated as follows. First, convert the length to inches. 100 feet times 12 inches per foot equals 1200 inches. Next, calculate the temperature change. 120 degrees Fahrenheit minus 20 degrees Fahrenheit equals 100 degrees Fahrenheit. Then calculate the expansion. 0.3 times 1200 inches times 100 degrees Fahrenheit equals 3.6 inches. This means that the 100-foot length of PVC conduit will expand by 3.6 inches when the temperature increases from 20 degrees Fahrenheit to 120 degrees Fahrenheit. To accommodate this expansion and contraction, expansion joints must be installed in the PVC conduit system. Expansion joints are designed to allow the conduit to move without putting stress on the system. The NEC requires that expansion joints be installed where the calculated expansion or contraction exceeds 0.25 inches. Expansion joints are typically installed at regular intervals along the conduit run, and the spacing between expansion joints depends on the temperature change and the length of the conduit. The NEC provides tables that specify the maximum spacing between expansion joints for different temperature changes and conduit sizes. In addition to expansion joints, other methods can be used to accommodate expansion and contraction in PVC conduit systems. These methods include using expansion couplings, expansion fittings, and flexible conduit. Expansion couplings are designed to allow the conduit to move in a linear direction, while expansion fittings are designed to allow the conduit to move in multiple directions. Flexible conduit can be used to absorb expansion and contraction, but it must be properly supported to prevent sagging. When installing PVC conduit, it is important to follow the manufacturer's instructions for expansion joints and other expansion fittings. The manufacturer's instructions will provide guidance on the proper spacing and installation of these components. It is also important to consider the ambient temperature during installation. PVC conduit should be installed at a temperature that is close to the average temperature for the area. This will minimize the amount of expansion or contraction that will occur after installation. In summary, expansion and contraction are important considerations when using PVC conduit. By understanding the expansion characteristics of PVC and using proper installation techniques, electrical professionals can ensure that PVC conduit systems operate safely and reliably. The NEC provides guidance on expansion joints and other expansion fittings, and it is important to consult the NEC when designing and installing PVC conduit systems. Additionally, when dealing with electrical installations in specific locations like Tampa, Florida, several environmental factors must be considered to ensure the safety and longevity of the electrical systems. Firstly, Tampa's climate is subtropical, characterized by high humidity, warm temperatures, and frequent thunderstorms. These conditions can accelerate corrosion and degradation of electrical components, especially those exposed to the elements. Therefore, it is essential to use materials and equipment that are rated for wet locations and are resistant to corrosion. This includes using stainless steel or aluminum enclosures, corrosion-resistant conduit and fittings, and insulated conductors that are suitable for wet environments. Secondly, Tampa is located in a coastal area and is susceptible to saltwater intrusion. Saltwater is highly corrosive and can damage electrical equipment and wiring. Therefore, it is important to protect electrical systems from saltwater exposure by using sealed enclosures, waterproof connectors, and corrosion-resistant materials. In areas that are particularly vulnerable to saltwater intrusion, such as near the coast or in low-lying areas, it may be necessary to use additional protective measures such as cathodic protection or epoxy coatings. Thirdly, Tampa experiences frequent thunderstorms, which can cause power surges and voltage spikes. These surges can damage sensitive electronic equipment and cause electrical fires. Therefore, it is important to install surge protection devices at the service entrance and at individual circuits to protect against power surges. Surge protection devices should be rated for the expected surge levels in the area and should be properly grounded. Fourthly, Tampa is prone to hurricanes, which can cause widespread damage to electrical infrastructure. The electrical system should be designed and installed to withstand hurricane force winds and flooding. This includes using properly secured enclosures, reinforced conduit supports, and waterproof connections. In areas that are prone to flooding, electrical equipment should be located above the flood level or protected by flood barriers. Fifthly, Tampa has a large population of trees, which can pose a hazard to overhead power lines. Tree branches can fall on power lines, causing power outages and electrical hazards. Therefore, it is important to maintain adequate clearance between trees and power lines and to prune trees regularly to prevent them from interfering with electrical equipment. Sixthly, Tampa has a diverse range of soil types, which can affect the grounding of electrical systems. Some soils are highly conductive, while others are less conductive. It is important to test the soil conductivity and to install grounding electrodes that are appropriate for the soil conditions. In areas with poor soil conductivity, it may be necessary to use multiple grounding electrodes or to enhance the soil conductivity with chemical treatments. Seventhly, Tampa has a growing population, which is putting increased demand on the electrical grid. This can lead to voltage fluctuations and power quality issues. It is important to monitor the voltage and power quality and to install voltage regulators or other power conditioning equipment to maintain stable power supply. Finally, Tampa has strict building codes and electrical regulations that must be followed when installing electrical systems. It is important to consult the local building codes and to obtain the necessary permits before starting any electrical work. Electrical work should be performed by qualified and licensed electricians who are familiar with the local codes and regulations. In summary, electrical installations in Tampa, Florida must take into account the unique environmental conditions of the area. By using appropriate materials and equipment, following proper installation techniques, and complying with local codes and regulations, electrical professionals can ensure the safety and reliability of electrical systems in Tampa.